Hello, and today we're going to go over the content for moments for A-level physics. So let's get started. So a moment is the turning effect of a force, and it depends on two things. So say we have a pivot point here, and we have a force being acted upon perpendicular over here. The moment depends on the distance between the force and the pivot point, and the magnitude of the force perpendicular to it. And the equation is given by the moment is equal to the force times this perpendicular distance. And if the moments aren't balanced on an object, then the object will turn. So if you have an object like this, and you have unbalanced moments, the object will turn. So now let's go on to the principle of moments. So the principle of moments states, for an object to be in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments. For example, say we have a body like this and a pivot point over here, and we know that we have a force of 400 newtons acting at 1.5 meters away. We know that we have a force of 300 newtons acting 1 meter away, and we have an unknown force F, which is 0.5 meters away from the 300 Newton force. So given that this whole system is in equilibrium, we can find out this force because we know that the sum of clockwise moments will be equal to the sum of anti-clockwise moments using the principle of moments. So what we would do is find the sum of clockwise moments, which would be using the moments equation, so force times distance, as we said before over here. So we'll do force 300 newtons times 1 meter, which is the one clockwise moment, and the other clockwise moment would be the moment of this force, which is just this force F times the sum of these two lengths, because we're looking at the point, the distance from the point of rotation, which would be 1 plus 0.5, which is 1.5. So we'll add them up. So we'll get F times 1.0 plus 1.0.5. And this would be the sum of clockwise moments. And now if we do the sum of clockwise moments, because we know this is equal to the sum of anti-clockwise moments, we know that the anti-clockwise moments would be just 400 times 1.5. And all we have to do with this equation is solve for F. And we would get F is equal to 200 newtons. Now let's look at the definition of a couple. So a couple is just a pair of coplanar forces. So what does this mean? If we draw it out, we would get a rod like this, and we would just have the same magnitude F, which is parallel to each other, but just acting in opposite directions. And this causes a turning effect on the object. And if we look at the distance between the two coplanar forces, and we can label that D, we can find that the moment caused by the forces would be, if we calculate, would be force on this side, force times the distance to the midpoint, which would be force times d over 2. And then because they're acting both clockwise, or they could also be anti-clockwise for a couple, but in this case they're both clockwise, so we can add them both up together, and they both act at d over 2 from the center. So the sum of the two, we would just get 2f d over 2, which we can write as fd. And this would be the moment caused by the couple. Also, it's worth mentioning that to find the resultant moment, you can just add up all of the forces times the distances to get the resultant moment. You can make your positive either clockwise or anti-clockwise, but make sure that if your positive is clockwise, to make your negative anti-clockwise. And if your negative is clockwise, make sure to make your positive moments anti-clockwise. And then you can just make sure to add or subtract them together. So for example, we were adding the moments here, so we get 2 clockwise moments, adds them together to find the resultant moment. But if we had an anti-clockwise moment, instead of adding them, we would just take away that anti-clockwise moment. So now let's go on to calculating moments. So when you are calculating moments, you should calculate them from the point of rotation. But if we have a system in equilibrium, you can show that it's in equilibrium from every single point. We can call these forces A, B, C. And if we take moments from 3 points, so we can either take moments from here, here, and here, just to show how they work, but we can also take moments from any point along the rod or the object. Let's call these points A, B, and C. So if we take moments from point A, we will see that B is an anti-clockwise moment and C is a clockwise moment. And if it's in equilibrium, we would know that the sum of anti-clockwise moments would be the same as the sum of clockwise moments. So the moment caused by B should be the same as the moment caused by C. If we look at from point B, you can also see that A causes an anti-clockwise moment and C causes a clockwise moment taking from point B. And if you take moments from point C, you can see that, so from here, that B would be a clockwise moment and A will cause an anti-clockwise moment. So in all of the cases, the sum of clockwise moments should be equal to the sum of anti-clockwise moments. For each of them, because one of them is anti-clockwise and the other one's clockwise for each of the 3 points, we can see that if the system is in equilibrium, we can prove it from the 3 points. So therefore, it doesn't matter where you take moments from, you can still prove that it's in equilibrium. And you can also prove that the forces would be in equilibrium as well if this is equal to, so the forces going upwards is equal to the forces going downwards. And you might have noticed that in each of these cases, we did not take the forces that act at the points that we were measuring the moments from. And this is because the distance from the point is 0. So we can just say that the force, because moment is equal to force times distance, and because our distance is 0, our moment will cancel out. So we can just say that our moment is 0 and not include it. Now let's move on to uniform rods. So when you have a uniform rod like this, and you have a pivot point here, when you have calculations of moments, you have to take into account the center of mass of the rod, because this has a weight component to it, which causes a moment because it is at a distance from the pivot point D. Because you have a force and a distance from a pivot point, you would have a moment acting from the center of mass of the rod, so you have to take this into consideration. This is the end of the video. Thanks for watching. I hope this was useful for you.